Start. Okay, so today is the last lecture we have in this series. So, as you can imagine, this is a complicated topic because we are trying to solve a big problem. People have worried about this problem for over 40 years. So far, we have set up the problem, like the Hawking puzzle and the entangled pairs, and we have to change the whole structure all the way up to the horizon. And then in ordinary gravity, there is no solution to the puzzle. We proved it was like a rigorous puzzle. There was no easy answer to it. But then we have been looking at string theory, which is itself a big complicated theory of quantum gravity. And now our goal is to use that theory of quantum gravity and to actually see the structure of what is happening inside a black hole. So that's why the whole thing is going to be complicated. But we are going to talk only in pictures the way we did last time. But even more important than last time is that you should stop me and ask questions, because what is written here doesn't have to make that much sense. But the idea of what is written here, that should make complete sense. Okay, so the equations are there just to show you what the structure of the black hole inside looks like. We don't actually care about the equations. We just want to care about the picture, and that's all that you have to take away from here. Okay, so let's look at the summary of what we were doing last time. We said string theory is not that hard to understand. The fundamental particles in string theory are all fixed. There is the graviton, which must be there in every theory of quantum gravity. But then there are also these extended objects like elastic bands. The simplest one is called a one brane. It's called NS1 for technical reasons. We don't have to care about it. It's a one-dimensional line, so we can also call it a string. A five-dimensional sheet can be just called a five brane. There are branes of other dimensionalities. Then there's a topological object called a Kaluza and monopole. But all these objects are there. And also there are symmetries in the theory that can map any object to any other, which means you can't make a theory which, let's say, doesn't have this guy or doesn't have this guy, because then some symmetry will break. And it will not be. It's just like if you have neutron, you must also have the proton. If you have the up quark, you must have the down quark, because they are part of a symmetry doublet. If you throw one of them out, the theory doesn't make sense. It's equally, you can't add anything to the theory, because then again it will not fit with something in the theory. So it's a completely unique theory. It has a string coupling constant, and the coupling you can make small or large, because the coupling is like a scalar field. It can have a small or a large value, and we saw that was very interesting, because at weak coupling you can understand everything. It's just like free particles, free strings and so on, and the picture was so simple, just a string carrying vibrations and all that. So you can count how many states you have. If you count the number of states, you can get at least the entropy. And then if you go to strong coupling, well, that's where the real mysteries are, because you want to make a black hole, gravity has to be strong. It's a unified theory of everything. So when you make the coupling strong, gravity will be strong. And now everything is interacting strongly. The strings are interacting strongly, gravity is strong. If at this point we can figure out the structure of the object, then we are done. Okay. So what exactly are we looking for? You can see why things are complicated. Firstly, we must have a lot of particles together. Like in the hydrogen atom, you have one proton, one electron, so that's easy. If I give the uranium atom, it's more complicated, 92 protons, so many neutrons, and then 92 electrons, right? So we need a large number of particles, because a black hole is a macroscopic object. We're not looking for 2 or 4 particles, large number n of particles. We can't be at weak coupling, because then there's no black hole. We have to be at strong coupling. And given all this, we still have to find the structure of this object. And now there are only two possibilities that we are looking at. Either the object we make, its size is going to be small, like Planck length or something like that, and then all around it is just the gravitational field, and that will look like the old picture of the black hole. All the mass is in the middle, and then there is a horizon, and we have already seen that leads to the Hawking paradox. The other possibility is that as we put more and more particles in the bound state, and as we increase the coupling, maybe the size of the object keeps growing. And then it may never become smaller than the horizon, which means you always get this big fluffy ball, and you never actually get a horizon, and that will completely change our picture of the black hole. That's opposite to the picture that Chandrasekhar postulated in the 1930s, because he said all the matter will collapse to a point. But maybe string theory is telling us it will not. And that's what we are really looking for. We are trying to actually make this bound state. You will see a very simple example of the explicit construction of the bound state. We will do the explicit construction for the simple black hole that Ashok Sen found. That's the first black hole whose entropy we had computed. I'll remind you how we computed the entropy. And then for that, we will make all the bound states at strong coupling. And we will find that they are not like all the mass in the middle and then empty space outside. We'll find they are like these big fluffed up balls. And we'll actually give the exact construction, the metric for what that thing is. Okay, so then in that sense we can understand what the black hole is doing. We said these other things. The string theory lives in 9 plus 1 dimensions. So if you want to see 3 plus 1 dimensions, the other 6 dimensions must be little circles, and we draw them like this. These are the non-compact dimensions. These are the compact dimensions. We already said the theory is unique, and then because theory is unique, if you want to make a black hole, you have to take the objects I had on the first slides, like gravitons racing around, or strings wrapped on something, or 5-dimensional sheets wrapped on this direction, and some 4 other compact directions I call T4. It's not easy to draw it like this, so the T4 sort of goes into the board if you like. We could take np prime number of these, n1 prime number of these, n5 prime number of these, and then make a bound state. Okay, so we talked about this in detail last time, so I'm not going to go through it in detail, but the bound state looks like this. Schematically, you can see I put them all on top of each other, so it's all bound. But then we want to count the entropy of this, first at weak coupling, and then the idea of counting the entropy was very simple. If you have a string and you want to add some momentum carrying gravitons to it, all you get is traveling waves on the string. And if you have traveling waves, there are many ways to put the same amount of momentum on the string. You can put it in one harmonic, k equal to one lowest harmonic, or the next harmonic, or the next harmonic, and each one has a different amount of energy and momentum. Your total amount of momentum is fixed, but you can partition it among different harmonics in many ways. So this is just elementary physics. If I gave you a string and I told you to put different amounts of the same amount of energy in it, you could put all in the lowest harmonic, which might mean 10 quanta of the lowest harmonic, or all in the second harmonic, which means 5 quanta of that harmonic, or 2 quanta of the lowest harmonic and 4 quanta of the next harmonic. You just have to add up to 10. So you have to add up these numbers. If you take, let's say, the first harmonic with n1 things, second harmonic with n2 things, third harmonic with n3 things, this is the total energy it carries, and that energy is fixed by how much charges we have given to the black hole. So we had some counting like this. I'm just going through it quickly without the details because this is review from what we did last time. It's just a counting problem, and which Ashok Sen started first. And the counting problem has an answer which is known from the mathematicians. If you're counting how many ways to partition an integer n, if I give you n equals 10 and I ask how many ways can you add up integers to get to 10, the answer is given by this number, where c is the number of directions in which the string can vibrate. Okay, so we said we did that calculation for a string which is bound to a 5 brane, can vibrate in 4 transverse directions. That's the 4. There are also fermions coming from supersymmetry. Each fermion counts as half a boson. So we said put c equal to 6. It's all very precise. String theory leaves you no freedom. And then we got an answer for number of states. If you put c equal to 6 here, you get this many states. And then you take the log of that, you get a prediction for the entropy. And so our pictured weak coupling was, you take all these branes, make a bound state. If you can't resolve the compact direction, just looks like a little blob with some mass and charge there, and then you can try to compute the metric such a blob will create by going to your GR book, and you measure the area of that. And the Bekenstein idea that area entropy is given by this mysterious formula A by 4G works out exactly down to the last factor of 2 and pi. The number of states here agree with the number of states here, and that's the famous work of Strominger and Waffa. It follows from the original work a year before by Ashok Sen, where he didn't have the 5 branes but he had the other 2 charges, and in that case also the entropy works out. So as we'll see, you could use either the old Ashok Sen black hole or this new black hole, and we'll work with the Ashok Sen black hole because it is simpler, and that's what most of the talk today will be about. But then one thing we noticed was we want to get back to the Hawking puzzle, and right now we are not there. And the reason we are not tackling that puzzle is that these black holes have mass equal to charge, and they don't actually radiate. So this is something that you can understand very easily. If I gave you a string wrapped in this room, and let's make it periodic, suppose it goes there and comes back, it's like a loop. If I put some wave going in one direction on it, the wave will just keep going. Okay, it can't come off the string, it can't radiate out. So why can't it radiate out? Because it has some momentum. That momentum is conserved. Okay, and the momentum is equal to the energy because it's like a massless particle going this way. So if the guy radiated, it has to come out this way. So it needs some transverse energy, but it already has that momentum, so it must have that much energy to maintain that momentum, and also needs extra energy. It just doesn't have it. So if wave is moving in one direction, it never comes out perpendicular to itself. But now if you take a string and you have waves going in both directions like I did here, well, that's like what happens for a guitar string. You have waves going this way and that way. So they are called standing waves because they go both ways, and now they can collide. The momentum just cancels. There's no momentum to conserve because it is 0. And the energy of the left plus the right, it can come off, and that's what happens when you hear a guitar string. The string sort of loses its energy and the sound waves come to you. It's exactly that process that we are looking at to understand black hole radiation. Everything was very pictorial and simple. It will continue to be pictorial and simple. If I have a left and right moving wave, just like a guitar string, they can collide and they can come out. If I can compute the rate of it coming out, that is the rate of radiation from this object. If I compute that, what should I go and compare to? I should go and compare to Hawking's radiation rate to know whether this is telling me something about black holes. I compute the entropy from the area by 4G mysterious formula, from the actual macroscopic counting of string vibrations, and they agreed. Now I'm trying to see if the macroscopic vibrations can collide and radiate at a certain rate, and I want to compute with the black hole radiation rate. Okay, so getting interesting, should we compute that? Okay, so first we have left movers and right movers. Can you first of all at least get the entropy to work? So people figure that out. If you compute the entropy of vibrations both left and right, there's a formula you can get again by counting just the vibrations of strings, and it again agrees with the area. The area is a little bit more this time because there's some energy coming from these guys, which we already had, and there's some extra energy coming from these guys, which we now have added up. So the area increased a little bit. So this increases. You can see this side had only this, this, and this. Now it has this, also this. Okay, both increase, but it again agrees exactly. Okay, so we are still in good shape. We understand the entropy is working. Now we want to see what's the radiation rate of this, and let's see how that will work. So I have left movers and right movers. We call them left and right. They're looking like up and down here. The standard terminology is left and right, but that doesn't matter. And so this can collide and come out like radiation. Some will be left here, next time that will collide and come off. Just like if you have a guitar string, you pluck it, some energy comes off, after some time some more comes off, in the end there's nothing left. That's the process of black hole evaporation. So how will you do this calculation? You don't have to worry about the formula because we'll say it all in words. You have to first take the number of guys coming from this side. Suppose there are 10 guys per second, like a flux. How many guys are coming this way? And suppose 10 guys are coming from that side. So there'll be 100 collisions per second. Right? You just multiply the numbers. If there are 20 guys coming from here, 30 from here, there are 20 times 30 collisions per second. Okay, so the rate of radiation is called gamma. And micro means just microscopic calculation. We're not looking at Hawking, but the microscopic details of the string theory, so we call it micro. So how many guys will be emitted per unit time? Number of guys emitted per unit time is denoted by the symbol gamma in particle physics typically, so we'll do that. It's the number of guys coming left movers, which is this way, number of right movers, which is that way, and then times the interaction strength. Right? If they just pass through each other, that's also possible, but if they interact left and right movers, then they can come off. So we'll have to calculate that, what's the probability of interaction, but that you have to do in any theory. You can have electrons going this way, electrons going that way. When they collide, you have to compute the interaction probability, and then you'll know how many guys will scatter. So then you have to compute this V, but after you compute the V, this kind of formula is standard in quantum mechanics. The reason it is mod squared, it's in quantum mechanics you always compute an amplitude, you square to get a probability. So if you want the rate of emission, you need the probability. So this is a schematic way that all things in quantum mechanics are done. The number of left movers, number of right movers, and the interaction probability. If you multiply them, you get the rate of radiation. This is the process. Let me see if there are questions about this. Is this completely transparent? So it's all elementary physics, same from your elementary quantum mechanics textbook, but now we are applying it to all this string theory and black holes and stuff. Okay, and then on the other hand, we have to compare it with the Hawking radiation rate. So if you do the Hawking radiation rate, this is a very different calculation. There's nothing colliding with anything, nothing coming from here or there. You guys remember where this came from? This came out of the vacuum. So you had the vacuum. We had this vacuum where the things outside were going to the right, things inside were going to the left. There was a harmonic oscillator in the vacuum here, and then they got decoupled, and we did some calculation like that. Just the vacuum spit out two particles. The vacuum was unstable, the vacuum spit out two particles. It's a very different calculation. But anyway, we found two particles, and you remember they were entangled with each other, and that was our problem. But the vacuum was unstable and pulled out two particles, so I've just drawn that picture here. So if you go to strong coupling, this looks like the picture. Strong coupling means when gravity is there, you're using black holes. This was a weak coupling calculation because it's just using the strings and vibrations like what you do in a quantum mechanics textbook. Remarkably, everything agrees down to the last factor of 2n pi. Okay, so what does this actually tell us? Well, it's just a little puzzling on the face of it, but it does tell us that we are probably on the right track to be using string theory for everything. We were already happy that the entropy agreed. We had that on the slide just before, that the entropies were exactly agreeing between this crazy gravity idea of area and the actual count of states. That beautifully agreed. It continued to agree for the things which had vibrations in both directions. And now we are finding that even the rate of radiation you compute by the actual weak coupling calculation of simple quantum mechanics is agreeing with this very mysterious Hawking process. There's an agreement of radiation rates. Okay, so it just means we are on the right track, but actually we are not. We haven't even addressed our problem yet, because our problem is still here. And you remember our problem, there's nothing wrong with this emission, because whatever information is there here just comes out here. Okay, so if this guy was, let's say, had some energy E1, had energy E2, then the emission will always have energy E1 plus E2. Okay, So whatever comes out depends on what is in there. Now that is how normal bodies behave. If you take a piece of coal and you let it burn away, the atoms that come out from the coal are atoms of carbon. And now if you take a piece of something else, maybe what is something else? Burn a piece of sodium, which also burns, then the atoms which come out are pieces of sodium. Okay, so what comes out depends on what you come in, and that's how normal bodies behave. That's why information is not lost. Whatever information was in the coal, when you look at the atoms coming out of the coal, you see the same information. Now black holes, we always had this puzzle that these guys are coming out of the vacuum, and when they come out of the vacuum, everything will come out. E plus E minus pairs, mu plus mu minus pairs, everything comes out just proportional to their energy. We talked about that right in the first lecture, that it's a thermal emission. So atoms of carbon will also come out, atoms of sodium will also come out, everything will come out. If it's heavier, the probability will be less, but that's the property of anything thermal. But everything comes out, and what the black hole was made of is never in the story. This is just coming out of the vacuum. So something is very puzzling about this. But let's see where we can go with this. We still have a problem that these are two different things, but now let's try to go there. We just noticed that if we just had these three, this is the formula we've been working with for entropy. When you have both left and right movers, you remember we wrote a formula like this, but soon people did this for many cases, and the answer always looks like this. Ashok Sen's answer looked like this. There were only 2 charges, this was the entropy. When you put 3 charges, Strominger had this entropy. People did that with 4 kinds of brains mixed together, then they got this formula. If you had both left and right movers with 3 charges, you got this. If you have both left and right movers with 4 charges, it look like this. You can see the pattern. It's square root of all the different kinds of charges you have. Okay, so that just tells you that all kinds of, and the radiation rates also always keep working out. So it doesn't matter which case we take, they should all have the same physics. So we'll go back and work with the simplest guy. This slide is only here to tell you why it's okay to work with the simplest guy and still hope that we are getting hold of the correct picture. Okay, so as we said, it doesn't help us with the information puzzle, because weak coupling, there is no entanglement or anything. You're not getting pairs, just one guy is coming out. So there's no entanglement problem which is growing and all that. It just, whatever is here just comes out. It radiates like a normal body, no problem of growing entanglement. And in the strong coupling picture, these things are coming out of the vacuum. You remember this guy was entangled with this guy. And so in the end, when the black hole evaporated, all these guys which came out, they were all entangled with something, but that partner has vanished. So now these things can't be described by any state. Like this guy is spin up, if the guy is down, this is down, if the guy is up, but the other guy is not there. So I don't even know how to call the state, define the state of this outside guy. So the same puzzle, I'm just repeating the problem. The rate of radiation is the same, but the method looks very different, and so we still have our information puzzle. In that, we are still back to square one. Okay, so our real question is, how can string theory help? Because strings are normally quite small, and if they are small, they're like Planck length or something in size. You have a big black hole, a solar mass black hole like this distance 3 kilometers. If you put a string there, it will also fall and go back to being a black hole. So how can string theory tell us anything new about a black hole? Okay, so now we are going to actually go and try to see what the inside of a black hole looks like, and that thing is called the fuzzball construction. So let's go ahead and do that. Let me just pause to see if there are any questions at this stage. Yes, please.
So in the previous slide, the cylinder that the cylinder is the space-time.
So this side, yeah, it's the space-time. This is the non-compact direction. This is the compact direction. There are 6 compact directions which are just curled into small circles. This is X, Y, Z, 3 non-compact, and time I am not drawing. Here I am not even drawing the compact dimensions, I am just saying the non-compact part of space. At weak coupling, it's all flat space, so I just drew it like this. At strong gravity, space-time curves in general relativity, so I am drawing that picture, and this is Hawking's picture, flat space far away, then it gets curved, then a horizon forms, and all the funny things happen. This is that picture. So weak coupling will change to strong coupling, but the compact directions are very important for showing where the brains were wrapped and all in the microscopic picture. Here we don't even see any of that structure, we just have a black hole, and we don't draw the compact direction because they're so small. This is what it looks like. This radius will be 3 kilometers for a solar mass black hole. This is the compact dimensions of space-time. This will be a few Planck lengths in size. So I know they look bigger than this, but that's just the picture. Any more questions? Yes. So the rate of radiation we compute here, ahead on this V, it depends on the coupling constant. It depends on the size of this compact direction which you wrapped it. It depends on the number of these green brains and the number of these blue things, the number of the red things. It depends on everything. Yes, right. So here this V depends on everything. The rho is the number of these guys. So the number of these guys depend on the blue things. This guy interaction strength depends on the string coupling G, which I had written before. It depends on the number of these brains, everything. But on this guy, when you compute this side, the one from the Hawking radiation rate, it actually also depends on everything. How is that? Because the mass of the black hole depends on how much, what you put in it, and we made it out of certain number of these, certain number of these, certain number of these. The size on which we wrapped it, it was an elastic band. So the longer the circle on which I wrap it, the more energy it has. So it's very funny, right? You put all those things in. This side of the calculation depends only on the mass and charge of the black hole. So it looks like a very different way of all those same numbers going in. There are actually 7 numbers in the story. There's the coupling, the size of this dimension, size of that dimension, the number of this charge, that charge. There are 7 parameters in it. So each side, even though I haven't written it, depends on all these quantities. And it's a very different calculation. And remarkably, these two things agree down to the last factor of 2 and pi. All those numbers, n1, np, all the numbers g, and the size of the compound, all of these go in here. They also go in here, and the number comes out exactly the same. So it's pretty miraculous, right? The process is so different here as compared to the process here. And remarkably, you do all this mess, completely different calculation from the Hawking calculation, which was harmonic oscillators breaking up like this, and the answer comes out the same. So doesn't that look surprising? Yeah, so it's just remarkable. It just tells you that string theory is probably on the right track, but right now it's completely unclear why it's working. Somebody else had a hand up? Yes, please. So nobody got it. People just said at strong coupling you expect gravity to work. And they said what you normally expect is that all the quantum gravity effects will be in a Planck scale around the singularity. I will change nothing else anywhere else and just write the picture from the GR textbook. So it's not like they computed anything at strong coupling. They just took the picture from the GR textbook saying that if the coupling is strong, you expect a big black hole, because if the coupling is strong, the gravity is strong. If gravity is strong, it will have a long range and there will be a big horizon, and the brains can't be very big. They must be in the middle, like a few Planck lengths in size. So then the rest of it is all empty standard black hole. They just took it from there and put it here. But just one second, just to say, that's exactly the step which will turn out to be wrong. The standard GR answer that you took the black hole to be the standard picture from the GR book, as we said before also, that's what will turn out to not be true. But here people just put it there and just observe that the numbers are working. Yeah, go ahead.
For entropy formula, like 2 pi root over in 1
Yeah.
if we include angular momentum also, like, will it be same formula?
It still kept working. So after this was done, right in the next year, later the same year, people did the thing with angular momentum. The formula changes a little bit, but it again continues to work exactly between the weak and strong couplings. I'm wondering if there's any chance I could find a pen here, or maybe a chalk. So the formula right now was 2 pi root n1, n2, n3. This is with no angular momentum. And if you put angular momentum, it is 2 pi root n1, n2, n3 minus angular momentum square. Okay, so for the macroscopic calculation of vibrating string, this is the answer you get. And in this case, if you compute the area of a black hole with this many much charge, you will get it. So this is equal to area upon 4g for this case. And in this case, you have to compute the angular momentum, the area of the horizon of a black hole with this charge and this much rotation. And you find that area, and again you get exact match.
Has the Hawking radiation calculation been done for the rotating case?
Yes, absolutely. And it continues to match. Absolutely. So that's the easiest thing to do, to just put the rotation in both sides, because simply means that you're not taking arbitrary vibrations going on both sides. The vibrations on this string that we had in that picture, these can be allowed to carry some spin, which contributes to the angular momentum, right? So the same way you made the entropy to work in this formula, you basically take these guys and you let them have spins pointing in a particular direction. That contributes angular momentum. Each spin has angular momentum half h bar. If the spins are random, half this way, half that way, the angular momentum will be 0. If all the spins are in one direction, angular momentum will be maximal, and you can do anything in between. So you have to do the same calculation for radiation. It's just that the spins had to be particular directions to get more angular momentum.
So it's an intrinsic spin of the string excitation.
That's right. That's all. The source of angular momentum here can only come from the actual spins of these guys. There's no other source of anything else. And as you know, angular momentum is spin, and that's where it's going to come from. There's no orbital angular momentum this time, because everything is stuck to the brains. These strings are vibrating inside the brains, which are all in the compact directions. So nothing is actually orbiting around like this right now, but the spin is there, and the spin contributes a half h bar for each excitation, and then it gives you the exact entropies and gives you the exact radiation. Yes. Say louder. Yes. Yes.
So why, like, in that case,
Yeah, so that's a good question. So the question was, let me just repeat the question. Among all these duality symmetries I was saying, which can allow you to interchange all the particles of the theory, there's one thing called S-duality, and it converts strong coupling to weak coupling. It might seem at first that this is very nice because we can compute everything at weak coupling, and then if some symmetry relates that to strong coupling, we will know everything at strong coupling. If that were true, we would have understood black holes long ago. It turns out it doesn't quite work like that. When you apply S-duality, it's true that the coupling constant changes, but the objects you have there, they also change. So if you had, let's say, a NS1 brane, what I wrote at the string, it changes to what's called a D1 brane. It remains one-dimensional, but the NS1 brane becomes a D1 brane. That brane has a different mass per unit length. Also at the same time, the size of the compact dimensions also change. The symmetry, some things happen. But in the end, it turns out you don't gain anything. Whatever difficulty you had before you change the coupling, you have the same difficulty now. Because what the elementary strings do at weak coupling, when they map to these things called D strings, they do the same thing at strong coupling. So it doesn't help. Something maps to something else, the coupling goes from small to big, but the objects you have go from these objects to those objects. These guys were easy to study at weak coupling. Those guys are easy to study at strong coupling. So that in some sense had to happen because there's a conservation of pain. I mean, the duality symmetry doesn't take you away from the difficulty of something. And that's the way it works out. Okay. But that's a good thing to think about. People struggled in the beginning a lot by trying to play with dualities and saying, can I get a good answer somehow? But it turns out after a while you realize, no, the things always work out in such a way that difficulty is the same. Okay. So we just said it doesn't help with the information puzzle. So now we are going to look at the information puzzle, and we said all the black holes are similar. So let's look at the one with two charges. And so let's go and remember that. Yes.
So on the slide, so for instance, the black holes where the N1 and N2 also have these N2 bar and N1 bar kind of things.
Yes.
So there also the Hawking radiation has been checked.
Okay. So it's very interesting. If you have just two charge guy, you can't actually put the bars in them to get the non-extreme. Okay, so this one, for example.
Yeah.
Yeah, so this is exactly the one for which it was checked, right? Because
I'm saying, but you also can have N1 plus square root of N1 plus square root of N1 bar kind of things, right?
Yeah.
So the entropy have been matched.
Yes. So the entropy has been matched, and the radiation rate, for example, works if you take root N3 plus root N3 bar and also root N1 plus root N1 bar. So if you do two of them, then it agrees. If you do all three of them, root N1 plus root N1 bar, root N2 plus root N2 bar, and so on, it has been quote unquote checked by a cheating. So cheating in the following way, you can actually, so let's suppose you take the completely neutral hole. So you know you can get a neutral hole if you take as many unbars as bars. Then you can do what's called a boost, which adds charge to it. So you can convert the neutral hole to a near extremal hole by boosting it. The near extremal hole answer has already been checked. So if you unboost, you can find the radiation rate from the neutral guy, and that agrees. Okay, but that's a bit of a cheat. Up to here, when you had two of them with the bars, there's a nice model, which Maldacena had of a string inside of 5 brane and so on, and the radiation rate from that, at least to leading order, seemed to work out. Okay. So things get more and more difficult as you put more bars in there, and less is known, but nothing contradicts. To whatever extent you can compute, it does work.
So, but even the Hawking radiation?
Hawking radiation, that's what I was talking about. The entropy works, but I was talking about the Hawking radiation. Yeah, I was talking about the Hawking radiation. So it's become more and more difficult. So when you have two root N3 plus root N3 bar and also let's say root N1 plus root N1 bar, you can only get the leading order Hawking radiation at low energies. That agrees down to the last factor of 2 n pi. But you can't get the whole gray body factor. Okay, so that's so that way. Yeah. Okay. So let's talk about a two-charge black hole. This is the work of Ashok Sen. So let's see what is happening here. So we have 10 dimensions, 9 space and 1 time. We make some of them compact, means they are circles. So there are 5 circles. One of them we call S1. You know, S1 is the notation for a circle. T4 is a 4 torus, which is just 4 circles. So really I should have said S1 and 4 more S1s. But since one S1 is particularly useful to me, we keep it outside, and then there are 4 more S1s, but we have just written it there. And you can see what this particular S1 is used for. That's the one I have written here explicitly. That's this S1. And on that I wrap some string, it n1 units of winding of the string, and I add some momentum mode to it with gravitons running around it, and I have np units. They are called p because they carry momentum. So np units of momentum, n1 units of string. You remember we did this 2 lectures ago. Okay, so now when we have this, what does it actually look like? If you open up the string, if I wrap it n1 times, and the length of this circle was L, if I open it out, the total length of this wrapping direction becomes n1 times L. I call it L total, which is LT. And then on that, if you want to see what this momentum modes are doing, they're just traveling waves. The same thing we have said many times before. So you know where all the entropy is. You can put the same momentum. You have to carry np units of momentum. You can put the same momentum in different harmonics and different shapes, and that's where all the entropy is. And Ashok Sen simply counted all the different ways of partitioning the momentum in different harmonics, and he got the entropy to work out. That's the one which gives this formula, root n1. I've called the 2 charges n1 and np, so it will be root n1 np. There are 2 charges, so you can call them n1 and 2, but they are more commonly called n1 and np. 1 tells you it's a one-dimensional string. P tells you it's carrying momentum. They're just nice names so that you know what you're talking about. But you count the number of partitions, you get the entropy, and this is the answer which you get. So this was Ashok Sen's work from 1994 December. Okay, but now we have a bigger task to do. We don't just want to count the states at weak coupling. We actually want to see what kind of structure do they produce at strong coupling. Like what kind of metric are they going to produce? Can we possibly work that out? Okay. So it's very interesting. We have to just understand these vibrations. So let's still stay at weak coupling and try to understand what kind of vibration the string has. So normally when you take an elastic band like a rubber band, you might have learned there are 2 kinds of vibrations which you learned in your BSc courses. One is longitudinal vibrations and one is transverse. So what is a longitudinal vibration? Longitudinal means you just sort of go like this, like sound waves. If I want to send a sound wave like this, I can compress the air here and stretch it out here, compress it here, stretch it out here. That's called longitudinal. So even a rubber band, you can make a longitudinal vibration on it. You can make the atoms closer here, closer here, further here. That is this picture. Okay. So if you, for example, I gave you a glass tube, you can actually excite longitudinal vibrations by just rubbing it with a piece of cloth like this. Okay, people do that experiment. And if you give it a kick this way, then it goes into transverse vibrations, and those are the transverse vibrations. There are 2 kinds. Now it's very interesting that the string theory actually doesn't have any longitudinal vibration. It only has transverse vibrations. And what's the reason for that? The reason is that if you have to have longitudinal vibrations, like a rubber band, it's made of atoms, and you can move the atoms closer or further, and that's what the longitudinal wave is. But a string is a fundamental object. It's not made from anything. It's not like it's made from atoms inside it. There's nothing to bring closer or further. It's just what it is, just a fundamental string. So in fact, this is what's called the no-ghost theorem of string theory. You go and try to compute all its vibrations. It only has transverse vibrations that transverse 8 directions. It actually doesn't have a longitudinal vibration. Okay, just something known about string theory, but the reason is also very physical, and that's going to be important for us. So why is that important? Because now you see, this is the radial direction for us. This is the non-compact direction. This is the compact directions. So the radial direction will be the angular, so I can draw an angular sphere, that's my theta phi. This is my radial direction away from the place where I put my central mass, and these are the compact directions which are very small. Okay. So now you can see if I only can make a transverse vibration, the moment I try to put any momentum on it to make the n1 and np charges, this guy is not going to stay at the same location. If I call this location r equal to 0, this is r equal to 1, r equal to 2, r equal to 3, the radial coordinate. You can see this guy is having to bend and occupy other values of r. That's crucial. So let me see if there are any questions about it. Because it has to bend in a transverse way, and the more momentum I want to put, the more I have to bend the guy. Okay, because if I make a small amplitude, I can't push much momentum on it. A big amplitude will carry more momentum on it. So this is again all ordinary, you can do it with a guitar string. Here's the guitar string. You want to send a big traveling wave. If you want to send a lot of momentum, you have to give it a big shake, and it's going to go like this. So more momentum means more amplitude. So you can see if I want more entropy, I need more NP, and I'm going to get more amplitude. Okay, so if I try to make a bigger hole, I'm going to put more N1, more NP. I'm going to make a bigger object. The bigger the object I make, the more this guy is going to vibrate, and you can see the bigger it's going to get. And that's all there is to it. I'm actually going to find the metric created by a vibrating string, which is carrying a winding of N1 and a momentum of NP units. And the guy is going to spread for the reason you are seeing right in front of you. And we will find it always pressed to a size which is equal to the horizon size, which corresponds to this formula of entropy. This formula of entropy tells you area by 4g, some horizon area, that gives you some radius of the horizon. It will spread to just around that size, and so there will be no horizon. That's where we are going, and this will just take us a few slides.
When you say size, you're also including the alpha prime correction. So you only measure the top of the size.
So that's a very good question. We didn't actually put the alpha prime correction in the beginning, but later we came and did the alpha prime corrections in later papers. And I will actually say something about this. So what happens is that, as we said, you can put the momentum in different harmonics, right? So then what happens is we start with the simplest case. What's the simplest case? Let's put it all in the lowest harmonic. Lowest harmonic means one oscillation like this, right? If you put all the momentum in the lowest harmonic, to carry NP units of momentum, you need a very large amplitude. Okay, because high frequency guys carry more. One quantum of high frequency carries a lot of momentum. If I put all in the lowest harmonic, I need a pretty big amplitude. If you take the guy with the lowest amplitude, the amplitude is so big, the size of the object becomes so big, much bigger than this horizon scale we are looking for, that the alpha prime correction is not even relevant. Okay. Next you say, okay, let's look at something with second harmonic like this. It's still pretty big and the alpha prime correction is not relevant.
I was also concerned about the dual gravity solution. That has zero horizon size.
So in fact, we are going to make the gravity solution. It's not dual, this is the gravity solution. So when I find the metric of this oscillating string.
I meant to say when the coupling is stronger,
Yeah.
you have a back reacting solution which has zero horizon size. That's what you were comparing against.
That's what I'm compared against,
So,
yes.
I mean, that has zero horizon size. So what would be the thing that you would compare on that side? That will have some alpha prime.
It will have alpha prime corrections, and what we'll find is whatever that thing becomes after alpha prime corrections, before you reach that place, the metric is modified by order 1. That's what we are going to see. So what happened was, when Ashok Sen was doing this work, on the macroscopic side, he did this calculation of counting the vibration states at weak coupling, and he got this answer. So we've all agreed with that answer. At strong coupling, he didn't worry about what the string was doing. He took the spherically symmetric black hole. Let me just go back to that picture. He took the spherically symmetric black hole like this and measured its area and did the comparison. Strominger-Waffa was just an extension of that, but Sen basically did this. What we are going to see is this picture is not correct. We don't actually get this at strong coupling. So that's where we are headed. So let's see what that tells us. So now we are looking at the shape of this. At weak coupling, Ashok Sen was just counting the number of these vibrations. But the interesting thing is we can actually compute the metric produced by this at strong coupling. And let's see what that is. Right now we just observed that because the transverse vibration, the guy is going to have a size. Now let's see what the size is. So the picture looks like this. In Ashok Sen's picture, he said, I have winding. You remember string winding looks like this. He said, I am carrying momentum, so he just drew an arrow for it. Well, I'm drawing the picture, but here mentally imagined the arrow. So he said, if we don't resolve the compactation, it looks like a blob here, which carries winding charge and momentum charge, and I have spherical symmetry around it, and then he said the naive geometry would be like this. If I put some quantum corrections, it becomes a horizon, but anyway, he took a spherically symmetric ansatz. And everybody had been doing that all through history. When they want to write down the metric of a black hole, the first thing they said, let's assume the ansatz of spherical symmetry. You've seen that in textbooks. So if you put spherical symmetry, the metric is only a function of R. If you write down a metric which is a function of R, you get the normal metric which is coming like this, then there's a horizon, then there's a singularity, and everything is spherically symmetric, but you have a singularity. But you've already seen something. None of the states that you can possibly make can be spherically symmetric. Because if I gave you a string, let's say stretching from the bottom of this floor to this ceiling, and I tell you to put some momentum on it, you're of course going to wiggle the string to send the wave on it. Well, how can you keep it spherically symmetric? It could be spherically symmetric only if you put a longitudinal wave. This is spherically symmetric because spherically symmetric is in this direction, right? This would be spherically symmetric, but there's no longitudinal wave. The moment you have to make a transverse oscillation, it's not spherically symmetric. So the problem was the ansatz was not correct. If you first put a spherically symmetric ansatz, you do get the metric that everybody was using. It sort of looks like this. But now we'll see what actually happens is the following. This is the profile I've chosen for some profile I drew. This was the opened up space. You remember L total was N1 times L. I opened it for convenience. After every distance L, it's actually periodically identified, right? So this is a compact circle from here to here. This opening was only for my convenience. So what does the string actually look like? The piece from here to here, this piece just gives a strand like this. Can people visualize that? Then this piece from here to here gives this strand. This piece from here to here gives this strand. So you can see that if this is just a picture in the opened up thing, but what's really happening is the string has a winding of N1 units. So the number of these guys will be N1. They're not at the same place because the string has a vibration profile. So out of these N1 units, there are N1 of these pieces, but this piece is here, this piece is here, this piece is here, and so it sort of spreads out like a slinky. In the real space, string was wrapped like this before it had any vibrations. The elastic band is sitting at one place. If you put vibrations in it, the elastic band sort of goes around like this. That's easy to visualize, nothing to do with string theory. This is exactly what you would get if you take a rubber band, put a vibration on it, and rubber band had winding of 20 units, you put vibration, the 20 parts will just spread out away from each other. Opening it up just makes you see what the profile is, but really in real space, it just opens up like a slinky, that's the profile. So now if you compute the metric of this, it will still be flat space far away, nearby it will start curving the space, but when you come here, it's just like an extent of, there's no point singularity here to give you a spherically symmetric solution with a singularity. It just opens up to something nice. It just gives you something spread out. And something spread out doesn't actually create a horizon. It doesn't create a singularity. So let's see how you actually compute that. The metric of just one strand of a string standing there not vibrating, it was known. It's known by from a long time from the cosmic string people. They worked out the metric for a cosmic string. In the string theory thing, it was done by Harvey and Dabolkar. Called the Dabolkar-Harvey metric for a string standing like this. It's interesting that if you can, now this is that strong coupling. A string carrying some gravity, when the cosmic string people write down the metric for that, they had the metric for a cosmic string with sort of flat space far away, then as you come near the string, it's very singular. So you know the metric for that guy. Okay. Then if you know the metric for a straight string, people also figure out the metric for a cosmic string carrying a wave. It's called the Vachaspati transform, after Tanmay Vachaspati who invented this. And there's a simple way to take the metric for this, make a simple change and get the metric of a cosmic string carrying a wave, and still at strong coupling, the gravity is not weak. You can still write out this metric exactly. Well, if you can write for one strand, it turns out it's very interesting that you can superpose many strands all carrying different shapes of the wave, and you can still write the metric for this. It's very beautiful. There's a way to superpose different strands and get the metric for a number of strands. But what do we actually have? We have a large number of strands N1, each of which is sort of going in a different direction, like they're traveling like this. But if we write the metric of all of those and just add them the way this technique tells us to, we will get the metric at strong coupling produced by the guy whose entropy we were computing. Because all the states, every state was given by a different vibration profile. That's all we had. For every vibration profile, we get something like this, a bunch of strands. If we can find the metric for all of these, and there's a way to add the answer between different strands, get the metric for that. In the limit of large number of strands, you can smooth them out and say you have a distribution, and you get a metric. And the answer looks like this. I don't want to read this. I just want to tell you that the answer can be written in a very compact form, in a closed form. And let's just at least talk about it. This function f of v tells me the profile. So this is the vertical line before I put the vibration profile. After I put the vibration profile, I have to just tell you how much I displace, displacement of the string from the mean. That function is called f. It's a vector because there are many transverse directions to displacement. There are 8 transverse directions, right? So it's a vector. It's a function of, this direction is called x. It's a function of x minus t because the wave is running at the speed of light in this direction, right? If I have a traveling wave, you guys know it's a function of x minus t. So that's the wave going to one side, a left moving wave. So that's the wave. So this tells me the profile of the string. You can choose any profile. Every profile is a different state. Okay, this is all we have to know. If I put that this x minus t is called v, you guys know this u plus t plus x is often called u and t minus x is called v. Okay, that's just notation. So I put that function f of v here. I compute this integral, and that gives me this function h inverse at some point x, this function k at some point x, these functions ai at some point x. I put them in this metric. H, k and ai appear in this metric. They also appear in the various fields. These are the fields charge. It's a charged string. It radiates some fields, so these are those fields. You don't have to, this is the coupling strength. You don't have to worry about this, but there's an explicit form, and that's the metric. Okay, if I have a metric, I can start playing with it. I can look at the metric and ask, does it have a horizon? I can ask, does it have a singularity? Okay, I can ask, does it have, okay, closed time-like curves? I can ask, in what region is this metric, spreading? And after that, it will become basically flat space or empty space. I can ask all those questions because we have the metric explicitly, and here are the lessons. First, there is no horizon. You play with this guy. What's the meaning of no horizon? You take any point in this space-time, at any point here, you have the full metric. You take any x or v or any point you have in space-time. You can find a path that goes all the way to infinity while remaining time-like. Right? So horizon means that if you are inside the horizon region, there is some region from which light cannot escape. That means no time-like or null path can ever get out of there. So it's not like that. There is no horizon. You can always get out from any point. So that's the first lesson. There's no horizon. Because you just get a spread out source. It's more like a star. If you spread out the matter over enough region, then the horizon doesn't form. It's a little bit like that. So that's a big lesson, because the whole point of a black hole from the time of Chandrasekhar was that there's a horizon. Once you come inside some region, the light cones turn inwards. That's how, because there was a horizon, we got this funny pair production, because inside that, the energy of a particle could be negative, right? So why was that possible? Because the mass was so concentrated in the middle that the gravitational potential energy became minus gmm over r, it became 2 negative. If the mass is spread out, like in the earth, the mass is spread out, then that doesn't happen, because as you come closer to the earth, the potential does become more negative. But after you reach the center, after you reach the surface, if you keep going in, it doesn't rise like 1 over r, because most of the mass gets left outside. So as you go to the center, the potential never rises too much. It's a finite value at the center of the earth. In a black hole, if all the mass was in the center, as you keep coming close, gmm over r was going to minus gmm over r was minus infinity. That's how the instability happened. Once things are spread out like this, it becomes like the planet, like any planet, like the earth. You never reach a point where the potential becomes so negative that you can actually make net negative energy states. So now there's no pair creation. All that mess that Hawking got is gone, because you're seeing all the metric in front of you, and none of them actually have a horizon. There's no place where you can get a negative energy particle. The pair creation thing is completely gone. Okay. Somebody had a question?
When we say that the solutions are not spectrally symmetric, so we mean in the bigger 10-dimensional space, if we take the position in 4-dimensional space, it is spherically symmetric.
So not really. No. In the 4-dimensional space also it's not spherically symmetric, because this x coordinate is in this transverse direction. So this is the 4-dimensional space, right? The non-compact dimension is this. So sometimes the string, so suppose this was in the middle of the hole, sometimes the string is going this way, sometimes the string is going that way, right? So suppose the string vibrates just in this plane, and suppose it doesn't go to that plane. Let me just take that example. This is x and this is y, all in the non-compact direction. So now the metric will be sort of spread in this direction, but I have just chosen something which is not spread in that direction. Okay, so it doesn't have to be spherically symmetric. I can take any profile I want. It is true that if I take something very generic, it will do all this. It will be roughly spherically symmetric, and that is true. It's the same way any planet is roughly spherically symmetric. Doesn't mean it's exactly spherically symmetric. There could be a mountain here and not there and so on. But it will be approximately, just because of genericity. But the point is, it is still spread out. That's the more important point. The moment it is spread out, the potential is never very singular, and the light cones never turn in. The whole black hole structure is gone. It's more like a planet. But yeah, it's not spherically symmetric, because this is the x over here. Yeah. Say louder, please. I didn't understand the question.
How do you get this metric exactly?
Oh, how do I get the metric? Yeah, so I didn't derive it for you, but all the steps are here. The metric of a single line, a string which is just standing in one place, a single string, was known, and it was given by some functions h, k and a, which had very simple forms. For them, this function h inverse k and a, the a was 0, the f you put equal to 0, this f you put equal to 0, 1 over x square. That looks like the kind of metric you get with a potential, right? So like for a point particle, the harmonic functions are 1 over r. 1 over x square just like 1 over r square. That's because there's an extra string and all that dimensionality. But the 1 over r square just like the 1 over r potential. So if I put f equal to 0, that's the metric for a string sitting just at one place at r equal to 0. R is the radial direction away from this. If I put r equal to f equal to 0 in all these functions, the integrals become trivial. There's no v dependence. They all become 1 by r square. Okay, so that's simple, right? And you put it in this metric, you get the metric for the string. Okay, the ai are not there because the f's are 0. So ai is not there, they are 1 by r squares. That's the metric of a string like this. The moment you put a wave on that string, now the wave depends on some profile function f of v. If I put that f of v here, you can see some place the f of v is going to the right, some place going on the left. So sometimes you get x minus f. The source is not at x equal to 0. It's not, x is the distance from the origin, right? It is x minus f, because the distance where the source is, that's why you're getting this. So just like a point particle, a charge was kept not at the origin but at some other place. It's simply a distributed charge here. So it's just like computing the potential of a charge, but the charge is spread over different places. And the integral comes because different parts of the wave are at different places. So you can completely make sense of this just as electrostatics. If I gave you a string carrying charge in electrostatics and told you write me the electric potential of that, you would write something exactly like this. Okay, so 1 by r, we have 1 by r square. That's because change in dimension. Okay, so but otherwise it should be 1 by r. Does that make sense? So that's the answer for one potential, for one strand. Now, if you have many strands, you have to add over all the different strands. That's what this integral is coming from. I'm adding over many strands. But after that, there is nothing else. You smooth it out and you get this answer. And then you just put this integral guy and you put it here. So it's just the same source, but again the answer was already, important thing was already said in words before, because the string is vibrating like this, sometimes going towards positive x, sometimes going to negative x, sometimes this way, sometimes that way. The source is spread out. It is not sitting at one point, the origin. That's the only thing which matters, and everything is just like electrostatics. Okay, so we said the first lesson was there's no horizon. Second thing is that spherical symmetry not obtained, and if people were getting the wrong answers because they assumed spherical symmetry and then tried to write the answer, then different microstates have different structures. So there was this whole thing, black holes have no hair, all black holes look alike, how can we ever count their states? But of course you can count them, they all look different. In fact, each one has you choose different profile f, it has a different metric, so you can just schematically say one metric is this one. So far away they're all the same. For a while they look the same, but then they start differing around here, and so every metric has a, so that you expect, right? If you have different microstates, they should have different structures. So we are basically writing down the actual structure of all the different states of the black hole. And notice there are no other states. This includes all the states, because all the vibration profiles are all the states we can make. If you have a string with some winding and you add some momentum to it, there's nothing else there in string theory except traveling waves on that string. The count is also correct. You can prove there are no other states. So this is all there is. Yes, please. Okay, so right now it is not easy to see it from here, okay? Because right now, because of this, it does look singular, right? And it is singular here in the following sense, that if you have a string here, if I make you a cosmic string, where was that picture gone? Even if I make you a straight line like this singularity at the line, just like if I gave you a charge in electrostatics, the potential looks like 1 by r. We are never going to change that. That singularity is here. But that's just because I have an electron, that will always be a 1 by r singularity. The point was, am I going to get a horizon? And the point is, it doesn't create a horizon. If I give you a point charge doesn't have a horizon. We always have electrons, but electrons don't have horizons. And the reason it doesn't have a horizon is that if you just had a point mass, that has a horizon. But a point charge doesn't have a horizon. And that's very interesting, because if you have any object with charge bigger than or equal to the mass, the electric field it radiates, you have to take that also into account, and the metric produced by the electric field it radiates. And of course the gravitational field is there from the mass. You put the two together, as long as charge is bigger than or equal to mass, there is never a horizon. Okay. Now remember, we talked about the fact that all the elementary objects in string theory are very beautiful. They all have charge exactly equal to the mass. There is no horizon. Okay. So you will always see sources. These are sources that happen here. And the sources are not horizons. Like if you have a string in this room, you will always see the charge, and the electric field will have a 1 over r singularity at the source, 1 over r singularity at the source of where the source is. But you will never actually generate a horizon. Again, all the properties of string theory are being used because the amount of charge is equal to the amount of mass. It never actually creates a horizon. But if looking at this, if you say, can I see there is no horizon? You can't. You have to play with it a little bit. You have to actually look at the metric. You have to actually take some point and draw a null geodesic, and you prove that it doesn't have a horizon. Yeah. So from this you can't see it. Pardon?
String theory cannot give any singularity the way you have explained that.
Yes. So it can only give these are not what we actually call singularities. If you like, it can only give the singularities which correspond to the natural sources in the theory. Like if the theory has a string, then at the string the electric field will go like 1 by r square. We don't actually call that a singularity because that is natural to any object of charge q. Then it will have a so, but any other singularity it cannot have. So it just has what are called the source singularities. But the point is that the source singularities, normally you might think that they can create a horizon if you put many of them close together. What we are finding is if you put many of them, it actually spreads out like this. And you, instead of accumulating at one point, it is spreading out over a lot of the space. That was this picture. It is spreading out like this. They're not all sitting at one place. And so all the individual sources, putting many of them together, does not generate a horizon. That's the lesson. Only. Pardon, say again?
The charge is equal to mass relation.
Yeah.
That is true for 4-dimensional black hole also.
Yes, so in 4-dimensional black holes, people already knew before string theory that if the charge is less than the mass, you get a nice horizon. Charge equal to mass is also okay. If you take charge bigger than the mass, you get a naked singularity. Okay, so charge, this was already known in classical GR. Okay. Now in string theory, all the objects have charge equal to the mass. So you can only make objects which have charge less than equal to the mass. Right? These guys have charge equal to mass because all the objects have charge equal to mass. If I take some strings and some anti-strings, like strings going this way and some strings going the other way, then the mass adds and the charge cancels. So I can always make charge less than the mass, but I can't make charge more than the mass. So it's a very nice, beautiful property of string theory that you never end up making what the GR people already knew were bad things. Charge bigger than the mass was a bad thing because it gave a naked singularity, but in string theory you can't make it anyway. So it's very nice. These guys have charge equal to mass, and because they're the easiest ones to make, they are the ones we are making right now. Somebody else had a hand up? Okay, good. So I'm glad we spent time on this because this was sort of the main step that we had to go through, because now we understand the structure of where all this is coming from, and we said different matrices have different structures, and that's basically it. So this is what we call fuzzballs. The different structures we get are what are called fuzzballs, and now we find that in string theory there is no horizon. Okay, so of course you can make more complicated cases. So far we have done only 2 charges. Then people start playing with 3 charges, and they made lots of states for that. Then you can have branes and anti-branes, those are called non-extremal guys and so on, so we can play with that. So I'll just take you through a few slides which will show you the kind of flavor of things that people did. And again, the thing, we only want to see the pictures. I'll have formulae here, but don't pay attention to them, okay, unless you want to ask something about it, and then of course we'll talk about it. So the reason we want to talk about Hawking radiation is that's the puzzle we are trying to solve. Like, where's the radiation? So in what we have right now, there's no radiation. And why is there no radiation? Because we said extremal objects don't radiate. We said this before. If I have a string which is only carrying a wave in one direction, like this guy is carrying a wave only in one direction, that's the easiest case to count, then the wave can't come out. I need waves in this direction and this direction, then they'll collide, then they'll radiate, so I have to go to that case. Right now we haven't done that because we did Ashok Sen's case, which only had winding and momentum in one direction. That was the easiest case. But now let's see if we can go to something which has Hawking radiation. Okay, so remember the story from before. At weak coupling, we have left and right movers, they collide and they can come out, all the story. And a strong coupling, we saw all this stuff coming out of the horizon. And this one has the entanglement problem, the Hawking paradox. So this picture maybe is not right. And anyway, now we now know from the work of the last 20 minutes, this is not the correct picture of the black hole anyway. Okay, there's something else going on in the black hole. So now what should we do to solve this problem? The weak coupling answer we know. At strong coupling, what we want to go is, now we know every state has a different metric. You guys know that, right? Every state had a different metric. So we should choose one particular state at a time. Then for that state, we should find the metric. It will not have a horizon. It can still radiate because it may have some instability, like the Earth doesn't have a horizon, but it radiates because the atoms are excited, then they can come to lower state, they go emit energy. We all know how the Earth radiates. So this object will not have a horizon, but will still radiate. And what we'll find is, whatever weak coupling calculation we did here, we have to do it for that particular state, and we'll do it. We'll find the corresponding thing here which will not have a horizon but some other structure. It will also radiate, and we'll see the two radiations agree down to the factor of last 2 and pi. Okay, so that's good. That means out of these funny fuzzballs we are finding, we are actually going to be able to get a radiation rate only for some very simple fuzzballs, because it's very complicated to do it in general. But that radiation rate will agree with this calculation which we had from the weak coupling. So that tells you that is in the right line of what we are expecting, and we see there's an exact match. So let's talk about that, about how it works. So the simplest case is where all the strings are not even joined into one string, they're sort of like separated out, and we have both left and right moving guys on it. The left and right moving guys, I can choose them all to be of the same energy, or you can choose it to be different energies. In a generic state, this may have energy 1 unit, this may have 3, this may have 2, this may have 7. That's what a general sort of beam looks like. Like if I said a beam of protons, they don't have to have the same energy. So a very generic state has all different energies, but because I'm trying to choose something simple, I'll give them all the same energy. Let's say 1 unit of energy this and 1 unit of energy on this. Can I do that? I can also choose their spins. Now these guys could be spin up, this could be spin down, pretty random in general, but I'll choose them all to have the same spin. So this kind of black hole has a lot of angular momentum here because they all have the same spin, all the spins align. Why am I doing that? Just to make something very simple. Okay, if they're all the same, then I can just compute for 1 and multiply by n to get the total rate. So I'll take something very simple. You don't have to look at this. It just tells you that we know if you want to technically write down this state at weak coupling, we just write it out in some form like this. These pluses mean the spins are all up, but you don't have to know that. Okay, this is just to prove to you that we do the work and don't do pictures all the time. We also work sometimes, and that's the state, but in pictures this is what it is. And we already said what is going to happen. On one of them, this and this can collide, and it comes out, and that is this picture. And we're going to compute the rate for that and so on. So that's what we need to do. Okay, but now we know that at strong coupling, this is a weak coupling picture. Hawking's picture was that you have a horizon there, and when you go inside, there will be a singularity. This is the usual picture of the black hole. But now we know that it will just end like this. There will be no horizon, no singularity. It is going to end like that. Okay. It turns out if you look at this particular case, in here there is a region which is highly spinning. Why is it highly spinning? Because the state I started with on this side, it had a lot of angular momentum because all the spins were in the same direction. So the gravity metric also to reflect that angular momentum is going to be the same. If it's 100 units here at weak coupling, it's going to be 100 units there because angular is just an integer times h bar. That won't change as you change the coupling. So it also has a lot of rotation. Rotation generates something called an ergo region. You don't have to know what it is. It's just something in gravity which tells you there's some very high amount of rotation there. Okay, just a property of the metric. So for this guy, this state, we can actually make the metric. So now it's state by state. Every different state of vibration here gives you a different state in the gravity. Of course, you're not supposed to look at this slide in any detail. Just to show to you again that we do some work. We actually calculate all the metric for this particular state with all the vibrations equal on the left and right, all of them the same energy, all of them is spin up. This is what the metric looks like. You can't see it from here, but it has no horizon. It has no singularity also. It just has is a smooth metric, and you know exactly the metric was worked out by these people, so we know the metric. Okay, with all these parameters, it's just showing you the metric. Now, in that metric, you have to go and compute the radiation. So we have two calculations to do. On the weak coupling side, we have to compute this emission rate. On the strong coupling side, we have to compute the emission from this metric, which is given explicitly here. And what we'll see magically is that they agree down to the last factor of 2 and pi. Okay. So we are really now taking something which doesn't have a horizon. It actually has the fuzzball structure we have found state by state, different fuzzball for every state, and for every state there will be a different metric. So here, if I change this to put, let's say, twice the energy here, or the spins in some other direction, there will be a different state. For that, there will be a different metric, and again it will match. So many such cases have been done by many people, and in fact, Amitabh Virmani, who's at CMI, some of you might know him, he has generalized this case to many other cases, and in each case you get agreement down to the last factor of 2 and pi. Okay, so here's the metric. And so now you remember how the calculation of radiation at this weak coupling is to be done. You have to keep the number of guys going this way. Those we call the left number of density of left movers, density of right movers, they collide, and then there's emission vertex which tells you what's the probability of interacting. I think this should be V mod square. I just called it V here, but you know exactly what I mean. Okay, but now we have to put the correct densities for our given case, and on a given case we have a certain amount here. I call them rho bar for the given case. This was normally just some random numbers, but I put the ones for all equal on this side and all equal. It's a very special case because I put them all in the same energy here. Normally if you have a beam coming, there will be some particle energy 1, some energy 1.5, 0.7, all that mixed up. It's normally a whole distribution, normally a Bose distribution or Fermi distribution of random quanta. But here I've chosen a very special state. They'll all have energy 1 here and energy 1 here, and I've called those distributions of energy fluxes as rho left bar and rho right bar. So the bar just means it's the particular one I want right now. But I know which one it is, I'm not telling you what it is, but you can see it in the pictures, all of them have the same energy, it's peaked at 1 energy. Okay, if they are peaked at 1 energy, the emission frequency is also going to be peaked, because if in this beam all the energies are 1 unit per particle, these are 1 unit per particle, emission will be exactly 2 units per particle. Okay, it's a little more than that because you have a spectrum. You can, if the energy was 3 and 3, you can either emit 6 or you can drop down to 2 and 2 and emit 2 units, like you come down to any low energy level. So you get a certain discrete set of emissions, but only a discrete set. Because energy, you understand that, right? If you have 6 and 6, total energy is 12. I can either emit all 12, or I can emit 10, or I can emit 8. I can emit all the way down to 0. So those are my spectrum. You can actually work out the spectrum. There's some complicated spectrum here, takes into account all the spins and so on, and you get some answer. That's easy to work out. And then you get certain distribution. I just don't want to take you through it. I just want to say that you can actually work it out. But it's just the collision. It's the kind of cross section you would do in any elementary quantum mechanics course. But now the funny thing is on the gravity side. On the gravity side, we said there's some region which is highly rotating. If it is rotating, it has an ergo region. In the ergo region, because it's spinning, there's something called frame dragging. The light cones turn around. It's just pictures. If you don't want to see them, you don't. But it's just that when things rotate fast, the light cones turn around, and that part of gravity becomes unstable. And it emits something just from the angular momentum. It emits something by what's called ergo region emission. There's no horizon, but you get some emission from a region which is highly spinning. It's something which is known in gravity. And if you do that, you can work out the spectrum by solving certain wave equations. It's a very different kind of calculation because you're solving a wave equation in this geometry, and you get certain frequencies of emission coming out. And it turns out the frequencies and the radiation rates are exactly the same. So down to the last factor of 2 and pi, you know, all these combinatoric factors and the 2 pi's and so on, the emission rates you got from that strings vibrating and emitting stuff, very different calculation from this huge spinning gravity solution, spitting things out and doing whatever it does from the gravity side. It agrees to the last factor of 2 and pi. Now this is not a generic black hole state. We took something very special. We gave it a high angular momentum because all the spins were in one direction. That allowed us to be axis symmetric. It's easy to compute when things are axis symmetric. Otherwise you can almost not compute anything. But for the case where you can compute, everything fits beautifully. As I said, people like Turton and Virmani have extended to many other cases, and in all cases the agreement is always perfect. Do you have a question?
So on one side you are computing the CFT calculation, that's the emission rate you're computing.
Weak coupling. It's the gravity emission from the fuzzball. For the fuzzball microstates, yeah. For the fuzzball microstates. So for these very, yeah.
What would be the sort of the, you know, what one would like to match with Hawking expectation also in some sense?
That's right. So
the average version.
yeah. So this is something, I'm glad you asked that because there's something I want to say about it. Let me put on the light and just tell you exactly what the significance of this calculation is. So I have until 5:30, is that correct? Yeah. Okay. Yeah, this is the real point we are making. So, you know, after this we can basically start winding up. So the idea is that on the CFT, it's easy to compute because it's all weak coupling, right? So weak coupling, just the strings and brains, we call this the CFT, but let me just say weak coupling. That's the language we have been using here. So let's talk about weak coupling. So at weak coupling, we just have some strings and they have vibrations going up and vibrations going down, and they collide and they come off, and that's the radiation rate. Everybody familiar with that one? Okay. I can do this for any state. And so there are two cases I do. If I do the generic one, generic means a typical state, these energies are split over all different energies. So I put Bose and Fermi distributions. Does that make sense to everybody? If I put a Bose and Fermi distribution, I'm taking a general sum of low energy, sum of high energy. The profile of these vibrations, they have all different energies on these strings, and they satisfy a Bose profile. Low energy, high energy, this is E, and this is the density of excitations, rho of E. So they are spread over all possible energies. And so radiation also comes out over all possible energies. It's a thermal distribution. If I put thermal set of vibrations going this way, a thermal set of vibrations going this way, what comes out is also thermal, because all possible energies here, all possible energies here, peaked at some energy. So what comes out is all possible energies peaked at some energy, and it's thermal. And this answer that you compute like this for the generic case exactly matches to the Hawking answer. So that was what I showed you before, that if you just compute the Hawking answer, on what should you compare it to? On this side there are many states possible, but you should take a generic state because you want to make the typical state. So if you put the Bose distribution here, it will be an exact match. That's the work from 1996. But this didn't solve our problem because these calculations are very different. This is strong coupling. It didn't really help us that much. It was interesting, but on strong coupling we had this picture. So we are getting pair creation, and we had the puzzle, right? Because the entanglement was growing here, it wasn't growing here. The problem was to see what happens at that end, but at least the numbers match. This is what we called gamma micro is equal to gamma Hawking. You guys remember me writing that. So that was the agreement which was observed long ago, but that agreement didn't solve the puzzle because that side has the puzzle. This side, of course, weak coupling, there is no puzzle.
Then my question would be, if you could put like a Fermi or Bose-Einstein distribution on the fuzzball profile somewhere, can you get the?
So we can't because we don't know how to do it. Okay, but that's what you would like to do. What we have shown is that here, if you don't take generic but you take special or a simple state. So simple means what? On this, let's say I put the same energy on each of them. So it's very sharply peaked at one guy. Then the radiation is not going to be a thermal distribution. If these have energy, let's say 12 and 12, or 6 and 6, I take an example, then the energy can only be at 12, 10, 8, 7. It's not a distribution, just like some particular peaks.
Not clear how to sort of distribute the geometry.
Yeah, so this is a very special geometry because I've done a very simple case, right? If I put some at energy 6 and some at energy 4, some at energy 3.5, it's going to be more complicated to make the fuzzballs, and we haven't made those fuzzballs. That's the problem, right? But for this guy, on this side, we actually know what the guy is, and we can see it has no horizon.
So, but the claim would somehow be that if you distribute it in some
Yes.
distribution, so the geometry should actually give you
That would be the claim. That would be exactly the claim. That's the claim. So all you can show is that if you take a simple one here, then on the gravity side there is no horizon. I shouldn't draw it that far down. This time there is no horizon. It looks like this. And the radiation from this guy is exactly matching to this guy. So if you take a simple case, you can do that side, you can do this side. It's both, there's no information problem because there's no horizon and the rates exactly agree. So the rates agree, whenever you can make a fuzzball, the rates agree with this calculation. If here you put a generic guy, it agrees with the Hawking rate. So the hope would be that when you take generic guys here, they would drop to exactly the Hawking profile because state by state it is matching. And if on this side you take a generic distribution, it has already matched the Hawking rate. But the difference is Hawking had a non-unitary process. Now state by state, the simplest things we are doing, they have no information puzzle because there is no horizon. So that's exactly what you should be asking. That's what I've put in this picture. We have a simple state. This is my picture of a simple state where the same energy on each string. You can see the energy, let's say 6 and 6 on each string. Okay, and that gives like this, and we can compute and we have an exact match. Now if you have, and that had an ergo region and all that, we showed that picture. Now if you take a more generic state, the states can all be different. Some have 2 windings, some have 3 windings, some have more energy, some have less energy. But then there are more, it's more complicated. Some will have, some region it may be spinning this way, some region it may be spinning that way. Okay, that's a more complicated geometry. But we can't make those geometries because they're not axisymmetric. If I take something that's spinning everywhere the same way, it has axis symmetry, you can make the metric. If something is spinning this way here and this way here, you can visualize it. But to actually write down the exact metric is very difficult. Okay, but the idea would be that in this case you would just get, emission from here and emission from here, and then in a generic case it would look like this, and then it would continue to match here. As to the radiation rate, we can at least see that when we go from here to there, qualitatively you can see you're going in the right direction. Instead of having these sharp peaks there, it is spreading out. But to actually do the calculation, we don't know how to do it. Right? But the idea is that for the simple fuzzballs you can make, the rates exactly agree between weak coupling and strong coupling. At weak coupling, if you replace them by generic distributions, it agrees with the Hawking rate. With those two, you can then imagine that if you take these, and these have no information puzzle, if you take these two more complicated things, you still have no horizon, but the rate will agree with Hawking. That would be is the hope, but that you cannot show because you can't make all the states. Okay, so now the conclusion from all this was that the actual fuzzballs radiate like a piece of coal. In a piece of coal, you remember there was no information puzzle. First one guy comes out and the entanglement grows, but then when this atom also comes out, each atom is entangled with its own photon. When the coal disappears, nothing is entangled with what's left behind. It's pretty much the same thing here. In ergo region emission, some part comes out, it leaves some part behind. After some time, that part also comes out, and the page curve first goes up, then comes down. Exactly what happens for a piece of coal, the same seems to be happening over here. Okay, so now let's see if we can just use the remaining 10 minutes to extract some physics lessons from what happened here. And the main question you should be asking is, how did the semi-classical approximation break down so badly? And so what that means is the horizon is as big as 3 kilometers for a solar mass black hole, is 10 to the 8 kilometers for a galaxy-sized black hole. These are enormous distances, and you would have thought that string theory, the theory of quantum gravity, should have no changes to the physics of what you expect from low energy physics, and yet we are saying the thing has completely changed. The whole interior of the black hole has changed. So across 10 to the 8 kilometers, quantum gravity has come and magically changed everything. And how can that even be possible? So we just want a qualitative understanding of why people thought that semi-classical gravity would be good. And that's obvious because the length scales were very long. And now we want to see why they turned out to be false. If somebody had a question? Yes, please.
Yes, sir. Why do we at all want to match the answer with Hawking's calculation? Because Hawking did the calculation with the Schwarzschild metric, but there was no description of the string version.
I agree. There's no fundamental reason why you should match it onto Hawking. Right? There's no fundamental reason because once you have said the inside of the black hole is not like what Hawking said, it could do anything it wants. The amazing thing is that if you go to this idea of black hole thermodynamics, the entropy, for example, it magically continued to match. The entropy comes from the area, magically matched onto the weak coupling thing which had no area or anything, just counter states. And the radiation rate that people computed from the weak coupling also magically matched onto Hawking's calculation. We didn't understand that either. They were just surprises. But given those surprises, we want to match it here with the exact fuzzballs once we got them. So recently, last year, I wrote some papers with my student Madhur Mehta, where we showed that any object, which doesn't have to have a horizon, if it has a very high redshift, it ends just outside the horizon, but has a very high redshift, it will actually have to have the same temperature, entropy, and radiation properties as the black hole. So these are actually all properties of high redshift. It's not a property of the horizon. So once you understand it that way, then you understand that any object at a high redshift will have to have these properties, and that's why it's magically all working out. Okay. So you can look at these papers. We call them extremely compact objects, or ECOs. So if you have anything which is sufficiently close to the horizon, we give the scale. If it's closer than that to the horizon, the size of the object, it can't actually stay there. It will collapse or readjust itself, its radius, unless its temperature and entropy and radiation rates are exactly that of the black hole. So there's a deeper reason for this, but we haven't talked about it. Okay, so let's see. What goes wrong with the classical picture of collapse? Chandrasekhar thought of taking a star. When it stops burning, it starts shrinking. It goes inside its horizon. Then the light cones sort of turn inwards. We talked about that in the picture. And then you get a horizon, and then you get pair creation. This is all the old story of the 1970s. What step in this could possibly go wrong? Well, so when you start looking at what we now have all these new structures we have found, these fuzzball states. You saw their metric explicitly. These are other configurations with the same mass and charge, and you have seen their metrics explicitly. Where do they come into the story? So the point is, you take your collapsing star, suppose this had mass m. We also have all these fuzzball states of mass m whose metrics I showed you, and you find there's a path to have quantum tunneling from here to here. So what is quantum tunneling? If you open your quantum mechanics textbook, you would see that quantum tunneling means you can go from one configuration to another one, by some kind of quantum process, and there's a path to tunnel. But the probability to tunnel is usually quite small. If you remember, that was an e to the power minus something is the amplitude. As you take the mod square, you get the probability, and the amplitude is usually quite small. That's why we call it tunneling process. But you can tunnel from somewhere to somewhere. You go under a barrier. You can go from one configuration to another configuration of the same energy. You remember, when you tunnel, you go from some energy back to same energy. In between, there is some complicated barrier, and the probability is therefore small, but you can tunnel. So it turns out there's a path to tunnel from here into one of the fuzzballs. And then you might say, okay, there is a path, but the probability will be actually very small, because little quantum objects do tunnel, like in alpha decay, a small particle can tunnel outside. But big objects don't usually have a very small tunneling probability. That's why I'm not tunneling out of this wall and going across. Classically, I can only go there and bounce back, which is what I do. But there is some small amplitude. I can tunnel through this wall and actually go outside. Okay, the probability of tunneling is very small if the mass of the object is much bigger than the natural scale, which is Planck mass. That's true. But there are many, many states that you can tunnel to. How many states are there to tunnel to? Each fuzzball, if you count them, you get the entropy. And the number of fuzzball states are e to the entropy, because entropy is log of the number of states. And if you remember right from the first lecture, we said the entropy of a black hole is actually very, very large. If you take the entropy of the sun, it has some entropy, but the entropy of a black hole with the same mass as the sun, if you compute from this a by 4g, it's vastly bigger. Okay. So how do you compute? What is the number of this number a by 4g stands for? It stands for the area of the black hole, which is 3 kilometers square, divide into cells of Planck size each. So if you take the size of the black hole, the g just means you, and the c and the h bar means you cover the whole surface of the black hole in little squares of size Planck's cell, Planck's length by Planck length. Planck length 10 to the minus 33 centimeters. The number of those cells, that's the black hole entropy here. That's the meaning of this formula. So you take the black hole area, and then you draw it into little cells of Planck length squared. So you can imagine how many of those there will be, right? Because each of them is 10 to the minus 33 centimeters by 10 to the minus 33 centimeters. And this radius is 3 kilometers. Whatever number of cells you get, that's the entropy, and e to the dat is the number of states. It's a very big number. Okay, so now you see the interesting thing. In any particle physics or quantum mechanical calculation, if you have some probability for tunneling to something, but there are many different states to tunnel to, you take the probability of tunneling to this state, you have to add to that the probability of tunneling here. So you can take the probability of tunneling to any one state and then multiply by the number of final states. You remember that from quantum field theory, you sum over final states, and that sum will involve a big number because it has e to the s Bekenstein states, and magically you find this smallness is of the same order as to cancel this bigness. Okay, so that's very remarkable. It's something which doesn't happen for the star or anything. A macroscopic object does have very small tunneling amplitude to go to some other macroscopic object, macroscopic to macroscopic here. But because the entropy is so big, you actually end up having a tunneling probability of 1. So here's a typical like quantum mechanical problem you can play with. Suppose you put a quantum inside a box, and you have a small amplitude tunnel into a neighboring box. Okay, so it will stay there for a long time and then slowly leak out to the other box. On the other hand, if I have many, many boxes it can tunnel to, suppose the probability of leaking to some box is 0.1% per second, then if I have 100 boxes I can tunnel to, what will happen after 1 second? the probability of tunneling out is order 1. So in 1 second, it won't be here anymore, it will disappear from here. And what you'll get is a linear combination of it being in all these 100 boxes. So it's an elementary quantum mechanical thing, but that's roughly what is happening. This shell is trying to collapse, but when it's here, it can also tunnel into one of these things. And so instead of ending up here, it actually ends up in a linear combination of all these creatures. So the black hole is not a classical object at all. What invalidates it from being a classical object is this very large Bekenstein entropy, which has been known to us from 1972. If you have many states to which you can tunnel, if you look at this picture, you simply can't keep this particle in this box. If I keep a particle in this room, and the walls are very thick, so there's only a 1% chance of, let's say, going out of this wall, but there are walls on each side, and there are 100 walls I can go through, suppose. It's an imaginary space, right? 100 walls to go through. The particle won't stay there. In time of 1 second, it will have gone either here or here or here or here or any of these 100 guys. So the state will be a linear combination of these 100 pieces, but there's nothing left here. Okay, and that's the magic. So if you just look at this tunneling thing, people have worked this out in more detail. We sort of gave an estimate as to why the numbers exactly cancel the the growing number with the large number of states and the smallness because of the smallness of tunneling. And then people have worked out special families of microstates and fuzzballs, and they can show that this cancellation happens. And so the black hole is a very, very quantum object. Okay. So let me skip the rest of it because I'm almost out of time. I want to end in 2 minutes. Let me just go to my last couple of slides and end here. What's the lesson from all this? So the main lesson we already said. This is not the picture of the black hole which has all the mass in the center, vacuum here, negative energy, pairs coming out. That's not the correct picture of the black hole. The black hole is this fuzzball mess for which we wrote down the metrics in these simple cases of Ashok's metrics. It just radiates like a normal body, and we even saw the radiation in special cases. So the whole picture is more like a star, and there is actually no puzzle, so that solves the information puzzle. And if you ask how did the structure change so much over a classical distance, we talked about this before. The natural length scale in quantum gravity, which you can make from c, h bar and g, is Planck length, which is very small. But if you want to make, and so that's why people were thinking that all the quantum effects can change the singularity from point like in classical physics to maybe Planck length in quantum physics. But that's not true. To make a big black hole, you need a large number of quanta n. The bigger black hole you need, the more number of brains you need to use or whatever. And so the way to ask what the length scale of quantum gravity, it doesn't have to be the natural things you make out of the fundamental constant of the units of length. It can be that, but it's also a dimensionless number n in the story. So you really have to ask if the quantum gravity effects are only across Planck length or some power of n times Planck length. And what we have seen from the fuzzball construction is that always some power of n times Planck length. And what does that actually amount to? It amounts to something of the horizon size. That you can see from the actual constructions. The scale, the size of the bound state actually increases with n and gives you something of the size of the horizon. So now just to end here, you can now ask what do we do with this? We solved the black hole puzzle, but it should tell us something about what to do in the future. And the most interesting thing is to go and look at cosmology. There are many puzzles in cosmology. Why is the cosmical constant so small? And what, for example, gives the energy required to drive inflation? There are many models, but I still find it a little puzzling. And there are all these troubles with the Hubble tension these days. The Hubble constant values are not matching. So these are all problems on the scale of the cosmological horizon. Okay. So what's the cosmological horizon? If you actually look at a picture of the universe, this is a slice at one time, let's say today, of the cosmology. Then there's a uniform density spread all over. And then if you ask what's going on there, it turns out if you draw the light cone structure, if you go up to the cosmological horizon, the light cones start tilting outwards. Okay, so that's interesting. That's the structure of the cosmological horizon. You can see it's very much like the black hole puzzle. In the black hole, the light cones all point inside the horizon. Outside the light cones are like this. Inside the light cones all point inwards. In cosmology, in the center of the light cone may be like this. As you go further out, the light cones point outwards. So once you go to the cosmological horizon, it forces you to go purely outwards. You can't even stay in here. Here, the light cone points inwards. You have to go inside. You can't even stay here. It's just the reverse in time. Okay, and also the scales are the same. If you just use the Hubble law, the amount of mass which is required to make a black hole of this radius here, if you look at the cosmological horizon, the amount of mass inside the cosmological horizon is just enough to make a black hole of horizon radius equal to this much. Okay, so it's the same situation, just like here the light cones go in, here they go out. If you just do time to minus time, like reverse direction of time, this problem sort of maps closely to this problem. So if we have found some interesting things on the scale of the black hole horizon, it suggests that we will find interesting puzzles on the scale of the cosmological horizon if we start taking the lessons here and applying it to this. And that's the kind of things we have been working with recently. in these papers we've played with what actually happens in cosmology, and we are finding that we can actually impact each of these puzzles. The answers here change by order 1, which is sort of what you need. You need some effects of order 1 to account for the funny things that you see. They're all at the right scales to give you new effects here, and I don't have time to talk about them, but if anybody's interested, we can certainly discuss that. Okay, so I'll stop here. Thank you. Okay, good question. Not to some particular state. As I said, it can tunnel to any of the states, right? Because if you have, like, example of this box, you can tunnel here or here or here or here, right? Like if I'm a particle in this room, it can tunnel out of this wall and go here, or tunnel out of this wall and go here. They probably don't have to be equal, depends on the state. Some state may be a little less, some state may be a little more. But roughly speaking, the number of states you have to multiply by the, roughly by the average number of states you have, and then minus the suppression, which is typically what the same state is, and then you get the cancellation. So it's not tunneling to any. That's what I said. If you put a particle in a box, and let's say I have 4 walls to tunnel, 6 walls of this room to tunnel out of. If I leave a particle here, after some time, what will the state be? It will disappear from here. Probability will go down to 0, and what I'll get is linear superposition of it being on this room plus that room plus the floor below plus the floor above. It's a linear combination of 6 states, because some amplitude tunnel on each direction. So if you do tunneling in multiple dimensions, that's what you'll find. So it won't. So the answer will be not any one fuzzball, the linear combination of all the fuzzballs. The relative weights can depend on which fuzzball, which linear combination of many fuzzballs. But the fact that they are all there, if you want the tunneling rate out of this room, you have to take the tunneling probability to this side plus tunneling probability to this side. You have to add all the 6 tunneling probabilities to get the total tunneling probability to exit this room, and that's what we are talking about. Yes.
All these possible states all the possible states that the black hole can tunnel into will have the same values for physical observables.
Same what?
Same value for physical observables. Like
yeah, so they're roughly all the same, right? Because they all have the same mass and charge and scale. But inside their structure is very different. We saw all the metrics, right? They roughly had this, they had the same mass and charge. All the metrics I wrote down for Ashok-Sen's black hole. But they all had slightly different structures. Some of the string was vibrating this way, some of the string was vibrating this way. So that's the way in which they differ. But macroscopically, they're all roughly the same. They're like different balls of wool, if you like. Strings are doing different things. Every different ball of wool is a little bit different, but has the same rough mass and same rough size. In that sense, they are like similar.
and if mass and charge is equal, then the mass is quantized for these states.
The mass is quantized for the extremal black holes, because if I have to make them out of the brains. I can take n1 number of brains. Each brain has the same mass, because just it comes of winding the length of that circle. So once I fix the length of the circle, and I can take n1 brains, and the n1 is an integer. I can take 1 brain or 5 brains or 99 brains, but I can't take 101.7 brains. So that way, for an extremal black hole, the mass is quantized. Okay. For non-extremal black holes, it's radiating. So somehow there's no well-defined mass, because it's not a time-independent state. It slowly keeps leaking. A little more difficult to define the mass. It's like a broad resonance because it's leaking. But yeah, at least for extremal black holes, absolutely quantized. Yeah. Somebody has their hand up? Yeah.
So for every fastball we have a unique metric.
Yes.
And by that metric we can calculate the radiation which comes up to the Hawking radiation.
Yes.
So can you say that every fastball structure will give the same Hawking radiation?
No, the details will be different, right? Because if one fuzzball is like something and some other fuzzball is like something, the details will differ. And that is very important, because that's how the information comes out. Like if you have one piece of coal of one shape and different piece of coal of slightly different internal shape, they should radiate differently. Otherwise, you will have loss of information again. So yes, it's very important that the spectrum I showed you before, it depends on exactly the excitations I took on it. If I change what's on it, like, I told you Virmani and all generalized the thing to different cases. In each case, radiation rate was different. It's the same on the gravity side and the weak coupling string side, but different for every fuzzball. Yeah, absolutely. It should be. Yeah.
So for black hole, classical black hole, suppose one black hole has some different fastballs than the other black hole.
Yes.
So the entropy of those two black holes will be different.
Okay, so then you have to ask what is the meaning of entropy. Because suppose you look at pieces of coal. When you ask what is the entropy of a piece of coal, One piece of coal is just in one state. That doesn't have any entropy. Entropy means how many pieces of coal I could have which have the same mass and size, right? So the entropy means all the different ways I could make the black hole. And that is a big number. Any one black hole is in one of these states. Every given particular black hole will have slightly different radiation, which it should have, and that's it. So when you give one particular black hole, you should not ask for its entropy. Like when I gave you any one of these metrics in that formula, that metric doesn't have any entropy. Right? Like when I wrote down this metric, if I choose one particular f of v, that is just one state. It's like one coal. One coal doesn't have any entropy. But all the different possible f's, that's where the entropy is.
And the radiation would be different or same?
Different. Absolutely different. So if I choose one f, it has a different radiation rate from the other profile f. Right? So every different shape will radiate differently, just like different pieces of coal do radiate differently. It's difficult to see the difference because the differences are subtle, but different pieces of coal do have different radiation. Somebody had a hand up here. Yeah.
Fuzzballs are quantum objects, so what if there are two fuzzballs far apart of, can they get entangled or something?
Yeah, just like anything else, because now there is no difference between a fuzzball and let's say a star or a piece of coal. Like there's no horizon, so everything like a normal piece of anything. I can take a piece of coal here, another piece of coal in that room, I can entangle them, I could use this in any one of the possible states, that in any one of the possible states. I can take a superposition, I can entangle them just like two electrons. It doesn't mean anything, it doesn't do anything for you. Like if you have entangled two pieces of coal, it doesn't do anything to the coal, it's just a quantum superposition. So you can do it, but it doesn't have any relevance to the problem of radiation.
So if different fuzzball radiate differently, so what is the meaning of matching with the Hawking radiation?
So the matching just means that if you take a very typical fuzzball, we took a very special one here, a very typical fuzzball should roughly match to Hawking radiation. Just like if I take a generic piece of coal, it should match to the black body Planck spectrum. If I take a slightly different piece of coal, it also matches the Planck spectrum. Now how can two different pieces of coal match the same spectrum? And the answer is because they don't exactly match it. One guy would be Planck spectrum plus little corrections, different coal would be Planck spectrum plus slightly different corrections. But on average, the profile has to fit. If I take a generic piece of coal, that's the normal StatMech story. It's exactly this story here. That's all we were trying to match. You had a hand up before that? Yeah.
So in this metric calculation, the source is string theoretical.
Yes.
Is the output that you produce the metric does not involve any quantum fluctuation. Once we have the input from the string, the rest of the calculation is classical GR?
Yeah. So in this metric, absolutely. That doesn't mean the fluctuations are not there. It's just that because the number of strings was very large, the object became basically classical. But there are definitely fluctuations around this. It's just like you're finding the metric of a very long string. There's nothing else to it other than the metric of a very long string. If the string is very long, it basically the quantum fluctuations sort of average out. So the classical metric is dominant part, but around it are always the quantum fluctuations. So we have done, stringy fluctuations, one loop fluctuations around this have been done. But the reason that classical metric is still a good way to write down the first answer to see the first level answer to see the structure, whether there's a horizon or not and so on, is because the numbers n1 and np were very big. If the numbers n1 and np were order 1, then you just have a fluctuating string and you need to worry about this thing is completely quantum. But the moment the number of windings is 1 million and the number of np is also 1 million, the classical profile is good and the fluctuations are suppressed by 1 over 1 million. That's all. Yes, if I make it very, very wiggly, I should worry about the fluctuations more, right? Absolutely. And so that's why we start with the one which has the simplest, all in the lowest harmonic. If you take it all in the lowest harmonic, the fluctuations are low, and you can probably see in what sense it is low. If you do these dualities, which you are familiar with, but other people may not be familiar with, and you map this thing to the D1, D5 frame, the one which has the singlest profile of one vibration, the lowest harmonic, it actually becomes the metric of ADS3 cross S3. So the ADS3 cross S3 is such a huge, empty, smooth space. It also has fluctuations, but the fluctuations are down.
His question about the fluctuations, there is the classical solution when there is a lot of fluctuation, there is a sense in which the quantum.
Yes, so the quantum fluctuation can be more for certain profiles as compared to others. And when the f of v is in low harmonics, the fluctuations are actually lower. And that's simply like saying that if you have the lowest harmonic, you need many quanta of that to make up the energy. If you have, let's say, 1,000 quanta of the lowest harmonic, you can carry the same energy with 1 quanta of the 1,000th harmonic. right? If I have 1000 quanta of the lowest harmonic, the fluctuation is always 1 over root n. They are 1 over root 1000.
So the typical fluctuation is it, does it have super Planckian curvature?
It's not super Planckian, but it is string scale for this guy, for this 2 charge black hole. And that's why you go to 3 charge, because you want to get away from the string scale. And in 3 charge, it's suppressed by string scale divided by the size of the 3rd charge. So the reason people were not happy with what Ashokson did and say, okay, story over, is that the typical guy still has fluctuations at the string scale. So you have to do the non-generic ones to say, I don't want enough fluctuation. And then when you get a generic one, you're getting stringy effects. But if the moment you add the 3rd charge, all the stringy effects are suppressed and you get the leading order answer for the classical metric.
But in the case of the recharge, that we don't have all the solutions.
Yeah, and it is still true. If you get to, by the time you get to generic solution, you will again have to have the fluctuations into account. That's always true. The generic state will always have quantum fluctuations. The whole point of the fuzzball construction is that it allows you to start with simple states and then go towards generic states. The simple states are the ones, for example, where all the energies are in the same harmonic and then the second harmonic, and you go to the higher harmonic slowly. So by starting with the lowest harmonic, you can actually see the metric, fluctuations are suppressed, look at the whole metric, just ask if it has a horizon or not, and you find it doesn't. Then you go to the next harmonic, like second harmonic, and you find, okay, still no horizon. Fluctuations, little bit higher. And then as you approach the generic state, you find, okay, I'm never getting a horizon, I'm just getting more fluctuations. That's all you can say, and you have to stop there, because by the time you get to the generic state, there are large fluctuations, and you can't have a good understanding in terms of classical metrics. The fuzzball method only shows you a path to approach it, which doesn't have a horizon.
In that case, is there such a path though? In the sense that like you start with the simplest solution,
Yeah.
and then there is a path towards generic states.
No, so that's exactly what would be very great to have. There are subfamilies known. So if you want like a lot of rotation or something, there are subfamilies known, but the generic state approach is not known. Right?
For example, the superstrata are not known.
So superstrata give you a large family. It doesn't give you everything. So there's the recent work of Pierre Heidemann gets you half the entropy. And he was saying over the summer that he can get of the order of the full entropy. But that he was trying to write the paper over this summer.
So this is the paper where the Schwarzschild.
Yeah, they're trying to make the Schwarzschild black hole construction. Yeah. So it's a very complicated construction, but with that construction, they claim that they have a way of understanding more entropy. But it's a little bit of a cheat actually in a way, because they're not actually making the Schwarzschild hole. They're making the Schwarzschild hole as a charged 3 charge black hole and an anti-3 charge black hole. So then the problem devolves down to understanding the 3 charge black hole. So in that sense, they push the problem away a little bit, but still it is what it is. Yeah. Yes. Yeah. That strings are what? Say that. Yeah. Yeah, so that's a very complicated process, and that's what we mean by the tunneling thing which I was showing you. Yeah, so this is very unclear, so we can only do very simple cases, like you're starting with a star, this has the atoms, this has only strings in it. So you have to see how you go from here to here. And so in these examples, we actually do that. You have certain strings, you send something in which is made of gravitons, and you have to see how gravitons coming from various sides. I mean, there are no atoms. In string theory, you start with the guys you have. So we can make something out of gravitons. You have to show how you're coming with 2 gravitons, and you end up with, let's say, 2 strings. So there is a path to go from 2 gravitons to 2 strings which are winding, right? So those things. So it doesn't matter. 2 gravitons can go to 2 fundamental strings. By the kind of S duality we were talking, they can also go to 2D strings. Okay, so you have to actually look at the tunneling paths for all these things. You can also go to 2 Kaluza-Klein monopoles, which is actually what was done here. So monopole and anti-monopole. So you're really looking for tunneling of elementary objects to solitonic objects. Right? So you can only show there is a path. Those calculations are very difficult. You can see there is a path, and then you just use the entropy argument to say that it could work, but very little is known about that. You can just show that the right order, but you can't actually do it.
So the metric that we got, the long big metric.
Yeah.
So is that equivalent to the Horwitz Polchinski action?
The metric we got, that long metric we wrote down?
Yeah, it gives the same results from that give the Horwitz Polchinski action.
Yeah, so the Horowitz-Polchinski is a slightly different thing. They were not trying to write down the metric for anything. They were trying to do the analog of the partition function to count the number of states. Okay, so if you do the partition function, you can't actually see any of the states, but the states they are trying to count, they should be like these states. That is true. So this is like a partition function way of counting the two charge states, and those states should be a little bit like this, like the two charge states. That is true. It's a partition function counting. So it's a little bit like the Ashok Sen counting, that he was trying to just get the count, but you can't see the states there. Yeah. So that kind of method should give the count of states. In some rough way, they should be like these states. It's not exactly these states because they are at a finite temperature. And at finite temperature, you won't get extremal states. You get non-extremal states. So those states were not, they were neutral states. So it's a little bit different. Counting the neutral states, there was something not quite right about it because they were looking at string temperature. If you have a string temperature, you're looking at neutral things at string mass. And neutral things at string mass are not exactly the Ashok Sen states. Okay, so it's not exactly the same thing, but it's the same ballpark.
If I have a single highly excited string, that can also count small black holes.
Yeah, so that was the initial idea when people started looking at these things. So people thought if I have a highly excited string, it should make a black hole. Susskind talked about that, actually, that's how the story started. And then it turns out that's not quite true. So Ashok Sen realized that, actually Waffa realized that you can only make extremal black holes that way, mass equal to charge. Okay, so then the string has to have all this winding, it has mass equal to charge, it can't radiate, it's extremal. And Ashok Sen made those and counted them. The Strominger Waffa made the three charge things which are extremal and counted them. Okay, if you want to make the non-extremal one, you have to have at least three charges. The non-extremal vibrating string doesn't actually make a black hole. So it's not that easy. It's not that easy to just take a vibrating string and you increase the coupling and makes a black hole. If you increase the coupling to make a black hole from a vibrating string, it always brings in one more charge into it. So the three charge guys, so the non-extremal holes you have seen, we talk about, they always had three charges. You might have seen this slide. If I have non-extremal, there are always at least three charges here. There's no non-extremal version of two charges. It's a very subtle point, but it's very important that you can't take the Ashok Sen two charge thing and actually make a non-extremal black hole. The moment you try to add enough energy to make it non-extremal, before that you always have enough energy to create the third charge. It's just something important to understand. It can exist, but it's too much at weak coupling. There's no black hole at that coupling. If you increase the coupling enough to make a black hole, you always end up creating a third charge. So only non-extremal black holes always have three charges in them.
So in the Chaudhary and your paper that you pointed out, that was three charge?
That was three charge. Yeah. All the radiation things were three charge. It was D1, D5, P and P bar. Yeah. It was three charge.
I have one question from the older picture.
Yeah.
The entanglement thing. So one of the particle go inside and another go out. So in that picture, the horizon still is there.
Yes, that picture of the horizon, that was the original picture of okay.
Yeah. So if the inside particle flips its sign, how does the information go out to the other particle outside?
If somebody flips the particle inside, it doesn't go out. That's true for any two entangled particles. If I have one electron, you have one electron, and we are in an entangled state, doesn't have to be inside or outside. If you flip your spin, I will never know. There's no communication between the two. So you can flip your spin, my spin will not flip because there's no Hamiltonian between them.
Yeah, but they are entangled, right?
They are entangled, but entanglement doesn't mean there is a Hamiltonian connection between them. So if you take one spin and you go home, it's entangled my spin and I go home. If you do anything to your spin, my spin is not actually going to flip or do anything. So if you make, let's say, lots of copies of the entangled state identically, if I measure my spin, it is half the time up, half the time down, I'll do some probability. You go home and you do something to it, you rotate it in a certain like or something, my probability will remain 50-50 because no effect has actually happened.
If one has done the result, then the whole state collapses.
Yeah, so that's the collapse problem. But that's why I said if you take a large number of them, with one state you can't ever predict anything anyway. If you make an ensemble of them but take a collection of them, my distribution function cannot be changed by you doing anything. It will remain 50-50. Yeah. That's the standard EPR paradox, right? Yeah.
Any other questions? Okay, if not, let's thank Samir for a
Okay.
very